In the last lecture, we started the concept of Bode plot. Although the idea of Bode plot and the mathematical foundation for it is relatively straightforward to understand, it is also very important that you understand what a Bode plot represents. To make sure that this is very clear, let's consider this example. We have a DC motor that drives a inertial load. The DC motor takes an input V, which is a voltage, and the output here will be either the speed or the position of the output shaft. For simplicity, we are going to neglect all the electrical properties of the motor. We are assuming that a voltage gives a torque to the load, and that relation doesn't have any delay or any transfer function between them. It's simply a gain. Of course, we know that that assumption doesn't hold true, but this is just for simplicity here. Let's assume that this motor is actuated with a voltage V that we are going to here choose to be a square waveform. We're going to apply V to the motor. Let's call that a V1, the magnitude of that input. We're going to hold that voltage at a constant value for a certain period of time, and then reverse the voltage to negative V1 and hold that for the same amount of time before again we switch back to V1, and so on. What happens to the motor? Well, if you turn the motor on by applying V1, the motor will start to spin in one direction. When you reverse the voltage, the motor starts to spin in the opposite direction. Easy. Let's call this time here T1, and let's call this time here T2. What is the frequency of this signal? The period is T1 plus T2, so the frequency here is 1 over T1 plus T2. So the greater the period, the lower the frequency, the more time the motor has to spin in one direction and in the other direction. The lower the period, the higher the frequency, the less time the motor has to spin in one direction before it has to switch to the other direction. Very well. Now let's attempt to draw a Bode plot of this that represents the output speed. Let's just start with the speed that I'm going to call here omega. If in this case T1 is sufficiently large, what happens to omega? Omega will start to increase and the motor will reach a maximum speed and then will spin at that constant maximum speed. So if T1 is around here, we give the motor sufficient time. We're assuming again that T1 is enough time for the motor to now speed up and reach that constant maximum speed. That constant maximum speed we are going to call here omega 1. So this is omega, the omega of T, the speed of the motor. What happens at T1? Well, at T1 we reverse the voltage, so the motor now starts to spin in the opposite direction. And again, T1 and T2 are the same here, so now the motor will reverse speed and eventually reach negative omega 1. Once at T2 we reverse the voltage again. So the speed of the motor will now go up and reach again the same value, and so on. And now it goes back down, and this cycle continues. The assumption once again is that T1 is sufficiently large to let the motor reach that maximum speed. And we reach the speed omega 1. Now we can attempt to draw some sort of pseudo-Bode plot that will show how omega 1 will change if we change this frequency, if we change the amount of time the motor has to spin in one direction or the other. We can now make a second plot where now the horizontal axis is the frequency. This one will also be the frequency, not time. And this axis is now the maximum speed we reach. If we're here at a frequency f1, and put it say here, we're going to reach a maximum speed of omega 1 right there. What happens now if we decrease the frequency? If you decrease the frequency, we are given more time for the system to spin. So this entire diagram is basically stretched to the right. T1 increases, T2 increases. Everything again expands to the right here. What happens to the maximum speed? It doesn't change. We are simply giving the system more time to develop the speed, but the speed will eventually go up and stay at that same speed. Alright, so even if T1 shifts to the right, the motor will go up and reach that maximum speed. So if we decrease the frequency, let's call that frequency F0, we reach the same maximum speed, omega 1. And if you keep decreasing the frequency, the same happens. You're just giving more time for the system, but the final value doesn't change. It always reaches omega 1. Now what happens if we increase the frequency? If you increase the frequency, we are now changing the voltage more often. Say in this case here, twice as fast. Let's call this frequency here F2. What happens here? Let's assume that F2 doesn't give the motor sufficient time to reach its maximum speed. So when you turn the motor on, it will start to go up. And when you reach now your new time here where we reverse the voltage, we will stop there and the motor will now go down in the speed and go in the opposite direction. We now reach here, this point, where again we switch the voltage and now the speed reverses. So now the speed goes back up and back down and back up and back down and back up and so on. We notice here that we reached a different value for the final speed. Let's call this value omega 2. Clearly, omega 2 is smaller than omega 1 because we are giving the system less time to develop a speed, and that time is not sufficient for the motor to reach its full speed. We are now going back and forth. So the motor, of course, the less time we give for it, the higher the frequency, the lower the maximum speed we reach. So now if you go at frequency F2, we will see that will start to decrease. And if you go now to a frequency F3, where F3 is greater than F2, that will further decrease. So here we have our omega 2. And you can see that this approaches the gain plot on a Bode plot. We have the magnitude of the output past F1 will now start to decrease. We assume that F1 is exactly the cutoff frequency of the system. Past that, now the system doesn't have enough time to develop the full speed, and the higher the frequency, the lower the gain. Why is this flat? Well, because if you decrease the frequency, we are simply giving the system more and more time, but it doesn't matter because you always reach the maximum speed. Hence this flat line. Very well. Now let's look at position, theta. Let's plot theta of t here. Same idea. We'll first look at the green line here. Well, to me it shows as green. I mean the first one I have, the one that we use for F1, given here. We turn the motor on up to a time T1 with voltage V1, and then from T1 to T2 we apply negative V1. What happens to the position? Well, the position, here we have T1, here we have T2, we will start to increase. After a certain transient, it will go up like that. And when you reach T1, now we will start to decrease and back up and back down and back up, of course with some transient. Let's assume that at this maximum position here that it reached, it was theta 1. We can now plot our function here, F1, the frequency, and the maximum position, let's call that theta 1, and this is negative theta 1. Here we are. Now what happens if you give more time for the system to develop its position? If we decrease the frequency, we again are increasing the time. T1 and T2 become larger. What happens to the position? Well, the position will keep increasing. Unlike the speed where we reach a maximum value, if you give enough time or more time to the motor to develop a position will keep increasing. So if the frequency decreases, this will start to go up and you keep going up, because once again, the lower the frequency, the greater T1 and T2, the more time the motor has to spin in one direction or the other before it reverses direction. And the position will always start to increase. So if you give it an infinite amount of time, that is, the frequency tends to 0, T1 and T2 tend to infinity, then the maximum position also tends to infinity. What happens if you increase the frequency? Well, we'll keep decreasing the maximum position we reach, because now we are simply doing the same that happened to the speed. Something like that. And this maximum value here, we'll call that theta 2, negative theta 2. So if you are at a frequency f2, then this will further decrease. And this will decrease now at a faster rate. And this faster rate will come from the fact that we just crossed the limitation here of f1, which came from the fact that we have inertia and friction. If you now pass to the frequency where we started to see the decay in a speed, the position will decay faster than before. So this slope will also change. Now we had one slope here, the slope will become steeper, because now we are at that famous frequency f1, where we started to notice that past that point, the system doesn't have enough time to develop its full speed. If we now take the integral of the speed that is reaching a lower and lower value, the position will result in a lower and lower value as well as we start to increase the frequency. So this slope now is a combination of the inherent slope that we see in the position that always goes up when the frequency decreases, plus the additional slope that comes from the mechanical characteristics of the system. This cutoff frequency here comes from the fact that our transfer function in this example would be the torque divided by Js plus B. We see a real pole, the real pole that we assume to be placed around this frequency f1. So now here we have the addition of, again, that inherent behavior of the system that keeps increasing the position if it has enough time, plus now the cutoff frequency that you see here that is affecting the speed. Now let's try to compare these two graphs. This is speed, which is taken from this transfer function. This is position, which is taken by integrating this transfer function. Right, the output here is the input is torque, the output is the speed. We see here a flat line. We understand why we have a flat line here, whereas here we have this slope that keeps going up. Where is that coming from? Well, here we have speed. If you want to go from speed to position, what do? We have to integrate it. And by doing this integration, we are actually multiplying this function by 1 over s and adding a pole at the origin. This pole at the origin adds this slope that is now constant throughout the entire frequency spectrum. And that's why now the slope that was 0 became non-zero here. We know that this is negative 20 decibels per decade. This slope just increased. It increased because we had the effect of the inertia and friction that resulted in this cutoff frequency, which is again there, but now in addition we have that slope created by the pole at the origin, which is the integration of this reflected there. And this now represents the Bode plot, or something that could be a Bode plot with further manipulations, which is the frequency response of this particular system. The difference is that, first of all, we are not using a square waveform in a Bode plot, we use a sinusoidal waveform. So all these waveforms that you see here are also sinusoidal. I chose to use a square waveform here just for simplicity, so it's easier to explain and easier to visualize. But in reality, this is a perfectly sinusoidal waveform, but it doesn't change the understanding of the concept. The second difference is that here we are actually doing 20 log of omega and here 20 log of theta. Now notice something else as well. Here in this transfer function, the magnitude of the input is already there. If we change the magnitude of the input from V1 to something greater than V1, what happens? Well, the magnitude here and here will increase, so the entire Bode plot will shift up. If you decrease the input magnitude, so we say like half of V1, then everything will shift down. Right? And it makes perfect sense. If we increase the voltage, the motor will spin faster. If you decrease the voltage, it will spin slower, so the maximum position and speed that it reaches is smaller. And that's a representation of the Bode plot. What can we conclude from this? Well, we'll notice that when you buy motors, when you buy electrical components for your robotics or mechatronics projects, they will all come with a Bode plot. And they are there for a reason. The reason is that their Bode plot tells you at what frequency those components will operate. Imagine that you want a robot to do some sort of pick and place task. And you want that to operate, that a pick and place will occur at a frequency of, say, 10 Hertz. If your cutoff frequency here is too low, say 1 Hertz, then you will have to increase the magnitude of the input by a very large amount in order to get the displacement you want at the output, the magnitude of that displacement or speed at that particular frequency. If your cutoff frequency happens to be at, say, 50 Hertz and you want to operate at 10 Hertz, then if you look at speed, you are fine. Within that range, the motor will respond properly, the robot will respond properly to changes in the input command. But if you now start to increase the operating input frequency, then the maximum displacement and the maximum speed of that robot will start to decrease fast, to a point where it's simply vibrating and not providing any useful displacement or speed. And the same can be said for electrical components. Especially for those that need to operate at a high frequencies, you always see a Bode plot. That Bode plot tells you or gives you an idea in which frequency range you should operate that system. Of course, you can always increase the input magnitude in order to get a larger output, but there's also limits to that. At one point, we'll reach a physical limit and the output of that system becomes so small that it's not useful. And that's why a Bode plot is very important. It has applications everywhere in electromechanical systems design.